Learning policies in simulation and transferring those policies to the real world is one of the most promising approaches towards data efficient learning in robotics. However, due to the inevitable reality gap between the simulation and the real world, a policy learned in simulation may not always generate a safe behavior on the real robot. As a result, during adaptation of the policy in the real world, the robot may damage itself or cause harm to its surroundings. In this work, we introduce a novel robot learning approach called SafeApt that leverages a repertoire of diverse policies evolved in simulation for safe multi-goal robot learning in a data-efficient manner. In this approach, we generate a large set of policies to achieve diverse goals safely in various simulated dynamics conditions of the robot. Given an arbitrary goal in the real world, the robot searches for the most promising policy in the set through real-world interaction. Thanks to the learned probabilistic reward model and the safety model, SafeApt ensures data efficiency and minimizes safety violations during real-world interactions. We compare SafeApt with several baselines, both in simulated and real robotic experiments. We show that SafeApt finds high-performance policies within a few minutes of interaction in the real world, while minimizing the safety violations during interactions. In this simulated experiment, the arm has to reach the blue dot while keeping the end effector away from the red unsafe regions. Here, the reality gap is simulated as the difference in the link lengths of the arm. We see that SafeApt finds high performance policy in about 7 trials or 35 seconds of total interaction while keeping the safety score above the threshold. In this simulated experiment, the asteroid lander has to learn to hover at a given altitude closer to the ground. At any point in time, the lander should not go below 40 meters of altitude to avoid safety violation. Here, the reality gap is the arbitrary gravity between the two domains. With SafeApt, the lander finds high performance policy in about 4 trials or 1 minute of total interaction on average, while maintaining safety during the interactions. In this task, the KUKA robotic arm has to learn to strike the hockey puck to place it on a given location on the table. To be safe, during interactions, the puck should not go out of the table. The reality gap here is due to the unknown friction between the puck and the table. We see that SafeApt finds high performance policy in about 13 episodes, or 2 minutes of total interaction on average, while maintaining safety during the interactions. We also implemented this task on a physical KUKA robotic arm. In all the 8 replicates of this experiment, SafeApt achieves much higher reward than the baselines while maintaining the safety constraint during the interactions. We believe that safe sim-to-real learning approaches like SafeApt can be useful in robotic applications where a small mistake by the robot can incur high cost, for instance in space or deep sea applications.